Hello everyone, today we'll talk about the problem Student Attendance Record 2. A student's attendance record is a string consisting of letters A for absent, L for late, and P for present. And we want the student to be present during lessons, but we are a little bit lenient. The student can be absent, but not for more than one lesson, so either the number of A's has to be 0 or 1. And also, student can be late sometimes, but they cannot be late for 3 or more consecutive days. That's also bad. Otherwise, the attendance record is good, and we are asked to count the number of good attendance records of length n. Now, the first idea when we look at a problem like this, when we want to create something of a given length or count the number of ways to create it, is to think about how we would do that element by element. In particular, if we have something of a given length, then how can we add another element to make it longer? And in this problem, this will indeed lead us to a solution. However, it may seem scary at first, so I just recommend indeed trying it. Okay, so what do I mean? I mean that if we have already a attendance record, and you want to add a new letter here, then how many ways we can do that? Well, it's not very simple, in that it depends on what we have seen previously in this prefix that we've got. So now, the first question that I want you to wonder about is how many situations can actually happen? How much information you have to have about these n-1 characters, so that here we can add another character and know in how many ways or what values for that character are possible of those three. Because of course, P is always possible, but sometimes we might be unable to add an A or add an L, and it should be quite simple to say when we are unable, especially of course assuming that those n-1 letters were already correct, so we don't care about incorrect prefixes. Well, the answer of course is, if it has an A here, we cannot add an A here, and we cannot add an L here if it ends with two L's. Then we cannot add an L. And that's all. And in that case, what we care about is only if it has an A, that's an important part, and ends in some number of L's. Those are the only two things we care about. And of course we don't care about P's, P's are okay. And now, to any prefix, we can always add a P. If it doesn't have an A, we can add an A. And if it ends in at most one L, we can add another L. However, one thing that we have to keep in mind is that we are solving this problem inductively. We assume that we've got something from the previous step, and we have to make sure that we give the same set of information to the next step. So, we care about this binary decision about A's. We want to have the number of those that have 0 A's and those that have a single A. And also this ternary decision about L's, 0 L's, 1 L, or 2 L's. So there are 6 possibilities in total. We have to know the count for all of those possibilities, but also, assuming that we're not already at n, we have to make sure that we also give the next step the totals for our current step. So we also have to calculate all those 6 possibilities. Right? So the Cartesian product of options for A, options for L. And now it is quite simple for all those 6 possibilities to calculate them based on those same 6 possibilities in the previous step. I encourage you to think about that. And now we can show the general picture, and then you can see in the code the actual specifics. And the general picture is that if A is equal to 0, then we can either keep it at 0 or we can turn it into a 1, and that's always possible. And otherwise, if A is equal to 1, it'll stay a 1. So if A is equal to 1, it stays a 1, nothing happens here. And now, when we turn A from 0 to 1, then also L becomes 0, because it doesn't end in any consecutive L's then. L equal to let's say some k, then we can make it either equal to 0, because we are present, and we then don't change the a, or we can turn it into k plus 1 if we're late, but of course that's only possible if k is less than 2. And that's all the transitions that we have to make. And now the code will just maintain those 6 numbers. So this is the number of absences, this is the number of consecutive lates at the end. And in every step we'll create that same array, but for all the attendance records that are one longer. So first of all, for every number of absences we can be present, which means that there will be no consecutive lates at the end, and any good number of consecutive lates at the end previously is okay, because we zero it out, so that can be 0, 1, or 2, that's okay. Also, for any number of absences, so this is this part, if the number of consecutive lates is either 0 or 1, then we can also add an additional late, so turn L into L plus 1, so that's part of the transitions. And then also, we can take any situation where we weren't absent and we had 0, 1, or 2 lates, and turn it into a situation where now we were absent, and then we have 0 lates at the end, because those are only consecutive lates at the end. And the last letter here is A. You have to make sure that we calculate it modulo. At the end we return the sum of everything, and that is the whole solution. And also one side note, since now you see that this is a very simple recursive relation, we can solve recursive relations with matrix exponentiation, because when you have some set of numbers, in this case you have 6 numbers, so you may look at it like having those 6 numbers here, and then you transform them into another list of 6 numbers, and this is a linear combination. So every value here is just some weighted sum of what happens here. Then, well, that's exactly what a linear transformation, exactly what a matrix allows us to do. So we can also see that this is multiplying by a matrix, either from the left, from the right, how you write it. And of course, if you want to multiply by a matrix many, many times to simulate many, many steps, then you can either do that, or you can take the matrix and raise it to the appropriate power. So in this case, we are happy with a solution that's linear with respect to the number of steps. But if, for instance, the number of steps was equal to 10 to the 18, then we wouldn't be happy with that. However, we can exponentiate a matrix in time that's logarithmic with respect to this n. So when n becomes very huge, then you can still solve the solution by just raising a to the power of n. And of course, the matrix n we have to write down in such a way that it indeed encodes all our transitions. So if you want to make sure that you understand what those transitions are, you can try to just write the matrix such that when you multiply those 6 numbers for the previous state, you get the 6 numbers for the next state.